So how do we analyze a circuit that looks like this? We know this is called a parallel circuit because the electrons can flow in more than one path. And so, for example, here, we know this is the positive side and the negative side of the battery. So the electrons are going to want to move towards the positive side in that direction, right? But what happens when they get to this point right here? Some of the electrons, they want to go around this way, so we know they're going to end up going here. But what's going to happen is some of the electrons are going to go this way and some of them are going to go this way. And the electrons that go this way are going to follow this path, the electrons that this way are going to follow this path, and they're going to meet up again here and then continue on their way over here. So because the electrons, the flow of electrons sort of splits and comes back together, what ends up happening is that there's less current flowing through each of these resistors. And this actually makes it easier for the current to flow through the circuit, as opposed to putting these resistors in a row or in series. And we saw that in class. So the question is, how can we find out the combined current that flows through this whole circuit? And we're going to do it similar to how we did it with the last lesson on combining resistors in series, how we sort of turned two resistors in series into one resistor with a greater resistance. We're going to see how we can combine these ones here. So let's just go straight down to this example. We have a resistor that is 100 ohms and 200 ohms in this circuit. And the way we do that, the way we combine them, we don't actually add them this time. So we're not adding 100 plus 200, because what happens, remember, is that there's actually ends up being less resistance than these two when we combine them. There's actually a formula that enables us to do this, and this you'll see it on your formula sheet. It says resistors in parallel, and the equation for that, actually I'm going to copy it down up here in 1 because this is the spot for that. So 1 over the total resistance is equal to 1 over resistance 1 plus 1 over resistor 2 plus 1 over resistor 3, etc. So however many resistors you have, you add the reciprocal of the resistance. And we're not going to go into why this is the case, but let's see the results that it gives us for this resistor down here. So we see that R1 down here is 100 ohms. These should have units, actually. These are in ohms and ohms. And R2 is 200 ohms. So what's the combined resistance going to be? Well, we're going to use this equation. So 1 over the total resistance is equal to 1 over 100 plus 1 over 200. How do we evaluate this equation? Well, we can do the right side, right? 1 over 100 plus 1 over 200. We could just do that in our calculators. You could also, simplify it as fractions, find a common denominator, etc. But just very quickly in our calculators, we can see that this side is equal to 0.015, and this side is equal to 1 over the total resistance. So this is not equal to the total resistance. This is equal to 1 over the total resistance. So in order to solve this equation, we basically need to flip this. In order to flip that, we have to flip the other side. We basically just flip both sides of this equation. We can look at the 0.015 as 0.015 over 1, and we flip both sides. So essentially what we're doing is, well, it's going to look like this. The resistance total over 1, I don't need to put that part, is equal to 1 over 0.015, which comes out to 66.67 ohms, if we round that to 4 significant digits. So what we've basically done here is if we turn this circuit into a circuit with one resistor that has a resistance of 66.67 ohms. So these two circuits are essentially equivalent in terms of the overall flow of electrons through the circuit. So the electrons through the circuit will essentially act as if there's one 66.67 ohm resistor in there. Notice how this resistance is actually less than the resistance of either of these. And remember, when you split the paths, it's actually easier for electrons to get through each of the resistors because it's like there's less electrons getting through, so they move through easily. It's less jam-packed in each of those resistors. So it makes sense that it's easier. So we can now that we know sort of the total resistance of this circuit, we know how to do this. Unfortunately, this question doesn't give us a voltage for the battery. Let's just, I'm going to pick a 9-volt battery for this. Okay, pretty typical battery. So now that we know the total resistance of the circuit, the current through the circuit we can analyze in the same way we did those problems yesterday. Just think of it in terms of this circuit over here, right? So we have a, what we can do is use Ohm's law essentially, and Ohm's law tells us that the resistance is the voltage over the current, or the current is equal to the voltage over the resistance. I is V over R. So with a 9-volt battery and a resistance of 66.67 ohms, we can come out with a current of 0.135 amps. Or if we round to two significant, well, this question doesn't really, it's not really specific about the number of significant digits we have, but about 0.14 amps. So there we go, that's our current through the circuit. Okay, so we have our current through the whole circuit. So basically what that means is that's the total current. That's the current that's flowing through here. Oh, sorry, we're going the other way. We're going this way, right, to the positive side of the battery. So this current is going to be 0.135 amps, and that's sort of the overall current. The next question is, how much current, remember what happened here. So we have 0.135 amps here. Some of the current's going to go this way and some of it's going to go this way. Can we find out how much goes each direction? So in order to do this, we can actually. It's possible. We have the tools. The way to think about it is to imagine attaching a voltmeter. Oops, let's do that in red. A voltmeter is a device used for measuring the electric potential difference of a circuit between 2 points. So for example, if I attached a voltmeter over here to this side and this side of the battery, so it's basically like a little device that's got two little wires, you attach to each side of the battery, and it's going to tell you that the voltage of that battery is 9 volts. So we could do that, and we could do that at any point in the circuit. So if I attach a voltmeter on either side of this resistor, what's it going to give us? Well, the thing about it is we're still sort of, it's the same as we were attaching it over here and here on the side of the battery. We're still attaching it to either side of the battery. It's just with longer wires. And the thing is, no matter where we attach it, here and here, or if we attach it, say, here and here, or if we attach it here and, actually, let me erase that. So here and here, how do I erase? Like that. Here and here. Or if we move this, for example, if we erase this one and we attach it here and over here, we would get the same reading because either side is like you're attaching it directly through the battery, to the battery. And because we assume that wires have no resistance, just to keep our calculations simple. So the point that I'm trying to get at in this complicated way is that, let me erase that without erasing those calculations below, is that the electric potential difference across each of these resistors is just going to be 9 volts. So it's like this battery, this resistor, the electric potential is 9 volts, and this one as well is 9 volts, because if I hook this up, instead of here and here, if I hooked it up to this side and this side, it's still like we're connecting it directly to the battery, right? There's nothing in between the battery and those points. So the electric potential difference of each of these resistors is 9 volts. That's how much is lost across each of these resistors. If we wanted to find the current through each resistor, we can just use Ohm's law. So I'm going to do this by looking at resistor 1 over here. So resistor 1, Ohm's law tells us that I equals V over R, right? And if we know the voltage across the resistor is 9 volts, and the resistance is, for resistor 1, is 100 ohms, our current for that resistor is going to be, what's 9 divided by 100? 0.09 amps, right? And then if we do the same thing for resistor 2, I know I didn't give you much space on this page, sorry about that, but we look at the voltage, again, it's a 9 volt drop across that resistor, and it is 200 ohms. So how much current is going to go through that resistor? Well, 9 divided by 200 is 0.18. No, that's not right. 0.045. Is that right? Let me check. 9 divided by 200. Oh, yeah, I did that in my head. I'm proud of that one. So that is how much current goes through that resistor. So basically this tells us, if we go back to our diagram here, let's try to keep that in the bottom, telling us that this path here, we have 0.09 amps flowing this way and 0.045 amps flowing this way. And then at the bottom here, down here, it's going to be the same thing. So we have 0.09 amps. So I'll just put that 0.09 amps here and 0.045 amps here. And the thing to ask is, what happens when those two combine? Well, if we just add those two up, those two currents up, right? If we add those up, what do we get? Let's try it. 0.09 plus 0.045 is 0.135. Does that number look familiar? It should. Look, that's the same current that's coming out of the battery. So it makes sense that this current gets divided up here into 0.09 and 0.045 and then comes back together to form the current again. This actually is an illustration of Kirchhoff's current rule. In the last lesson, we talked about Kirchhoff's voltage rule, but now we can talk about Kirchhoff's current rule, or current law. Kirchhoff's current law states current going into a junction equals the current coming out of the junction or leaving the junction. And what I mean by junction is any place where two wires meet or split up. So this is a junction right here, and we see that the current going into the junction, 0.135, and the current coming out of the junction, 0.09 and 0.045, those are the same as this when we add them up. And coming into a junction here, we have these two values, which leave with that. So essentially what this is saying is that current is never lost in a circuit. It can split up, but it always has to come back together before going into the battery, like that. So this is a useful tool for checking our answer again, because we can calculate these two values, and we should see that they should always equal this total value that we calculated over here of 0.135 amps. So there you go. It seems like a lot of work, but let's remind ourselves what we actually did here. We first of all, before we could do anything else, we needed to find the total resistance in the circuit between these two resistors. And we did that by using this equation here to combine them into one equivalent resistor. The equivalent resistor had a resistance less than these two because the flow for the electrons is actually easier through resistors in parallel. Once we found this resistance, we were able to calculate the total current in the circuit. So that means like the current coming out of the battery or going into the battery. And that was 0.135 amps. Last, we were able to see that the voltage drop across both of these resistors is going to be the same thing. So that enabled us to calculate the current through each resistor. Lastly, we realized that these two have to add up to our total current in the situation. So your next job is to go to the problems on the next page and give them a shot. So this is a very similar question to the one we just did. So see if you can figure out these answers here based on what we did. Question 2 as well, you should be able to do. It looks a little bit more complicated, but if you realize the only difference really is that there's 3 resistors. Each of them are in kilo ohms. So first of all, you're going to want to convert that to ohms, just a little heads up. The answers are here, so you can check them. But when we have 3 resistors, it's the same calculation as when you have 2 resistors. So you're going to use the same calculation as we did up here, but you're just going to add a third one, plus 1 over the third resistor. Okay, so you can add as many resistors in parallel as you want using that same equation. Okay, so give those, where are they? I know it's a little bit confusing here. So give those 2 questions a try.